No wonder. Florida. My car. Thank you.
I hope. I know it's all. This breakup wasn't even a break for me. It's like my college classes. I just signed so much work. I don't know what that was about. I was drowned. So ACT study, which is in applied to you today. Oh, geez, I was struggling, Sela. I didn't know what I was doing. And I was like, asking her, like, I don't know what common I was.
No.
And then I got like a little review text message that my application was complete like 3 days after I took it, and I was like,
I got that from like every school that I've been to.
yeah.
I realized that like I had to like.
See, I've never tried that. Yeah, I was like,
When I got that, I just emailed. Yeah.
I was so thinking. I do too.
All right, did everyone pick up a handout up here? Okay, so today we're going to talk about sketching derivative graphs. I'm going to skip this homework from the 11th. Maybe we'll come back and revisit some of these problems once we get into test review. But really, it's just putting together first derivative test and test for concavity and sketching the graph. You also get to have a calculator on the test, so you'll get to see what that graph looks like. I think we'll get a chance to practice that next week. So this is a big topic today, which is sketching a derivative graph. And this takes a little bit of time to get used to because the graph that we see in front of us is not the original graph. It's the F prime graph or even F double prime graph. And so the y-axis is representing something else other than position. And so it's just going to get a little bit, take some time to get used to. But the handout that you picked up is your homework. So what I decided to do was take the homework problems that were in your packet and space it out so you're able to actually kind of put work around it. So your homework, I think we can probably do some of it together in class. And then I attached the key as well, so it makes it easy for you to access to see how you're progressing. All right, so let's go to page 26. But just a quick note about this week and next week. So today we're talking about sketching derivative graphs. Tomorrow we'll talk about optimization. No AP practice, so I'll remind you to cross that out when we get to that. This will be in your packet, the homework. And then I should be able to get back your quizzes, if not tomorrow, then Monday. And then we'll have 4 days to do test review. I'll give you guys a test review packet. We'll start working through those. And then your tests over curve sketching, and then all the topics from the quiz is also going to be on the test. And then doing curve sketching, derivative graphs, and optimization. Those are going to be the 3 topics in addition to your quiz. That's going to show up on the test. And so that'll be next Friday. All right, so page 26. So this, what we see in front of us is our, we're going to start off more straightforward one way, where we're just going to create a sign line off our function graph. So this is our function graph here, f of x. We know, so the y-axis of our function represents the position of our graph. So what you see is what you get, right? This is a positive value. This is value of 0. There's a negative value of 0. So if it's above the x-axis, that means the graph has a positive y value. Below the x-axis means the graph has a negative y value. On the x-axis, my graph has an x-intercept. So if we were to create a sign line that describes the slope of our graph, let's do that. So your sign line off of your function is going to your arrows will match exactly with what the graph is showing. But first, we want to identify slope zeros, right? So where do you see slope zeros? What x values do you see slope 0? When x is what? 2, 3, -3, right? There's a slope 0, -3. Where else? -1. I know it's a little bit off, but I meant for it to land at -1. Okay. Where else? And at 1. Okay. All right. So what you see is what you get. To the left of -3, what do you see about your slope? Slope is what? Yeah, so positive slope. Okay, so I'm going to use an arrow pointing up to indicate how my slope is looking like. Between -3 and -1, what do you see? Decreasing slope. Okay, so I'm going to use a down arrow to indicate how my graph is moving generally. From -1 to 1, positive slope. And then from 1 on, negative slope. So the graph is going to rise, and whenever I see a tick mark, that indicates to me that my graph is going to level off. It's going to flatten out for a moment. It's going to rest for a moment, and then it's going to fall. It's going to flatten out, rise, flattens out, and falls again. Okay, so this is exactly what, so this is no challenge, right? We know whatever the graph looks like, that's how our arrow is looking. Okay, so now we're going to try to graph what an f prime graph looks like. And this is going to act as a bridge for us to build our f prime graph. Okay, so now this is my f prime graph. What's different about the f prime graph is that your y-axis now represents something else. The y-axis no longer represents the position or location of your function. It now represents the slope value of your function. It's still describing the original graph, but if something is describing the slope value, then you can expect the graph to look a lot different. So to help us remind ourselves what we're looking at, we're going to kind of label our axis. So anything above the x-axis is going to represent where my original graph is going to be experiencing a positive slope. So wherever my graph has a slope 2 or slope 3 or slope 1 or slope 6, it all has to land up here in this positive region. Anything on the x-axis is where my original graph is going to be experiencing a slope 0. Okay. Anything below the x-axis, my original graph, is experiencing a negative slope. Okay. So back to our original function graph. Where do we see slope zeros again? Slope 0 occurs at what x values? We just put them on our sign line here. Yeah, -3, -1, and 1. So they will go on our x-axis now. Instead of peaks and valleys, now they're going to be on the x-axis. So on my original graph has a slope 0 at -3, a slope 0 at -1, and slope 0 at 1. Okay. Okay, so now between to the left of -3, we want positive slope. So if we want positive slope, we want this graph to live in this region. Okay, so don't look at the shape of the graph. This shape of graph is rising, I know, but we want our f prime graph to indicate not the position, but the slope value. So it's going to end up looking like this to begin with. So I'll talk a little bit about that. It's like, this feels a little bit strange, right? This graph is rising here, so why is the graph falling? But right now, just match where the graph's supposed to go. These points are helpful because these act as anchor points. We know the graph is going to kind of have to thread through these points. So we know the graph has to come down because it has to hit that point. And we know it has to be above the x-axis because that's indicated with my sign line, positive slope to the left of -3. Okay. Between -3 and -1, I want negative slope. So negative slope needs to live below the x-axis. So the graph has to go down, but it has to loop back up because there's a point waiting for it. So I'll go down. It doesn't matter how far you go down, as long as you have the graph eventually loop back up. Okay. Between -1 and 1, where do I want my slope? Where do I want my graph to live? Above or below? Above, but it has to go up and loop back down, right? So I'll make it go up and come down. Okay. And then to the right of 1, above or below the x-axis? Below. Okay, so this is just a very it's not very specific. It's just very general graph. We don't have to be very specific about, oh, wait, this is slope 3, so I need to figure out where that slope 3 is going to live. It's more the general shape of this graph. So I do want to convince you that this does represent the slope graph of this original function. So this is just ballpark values, right? We know that this is not by any means accurate. But let's say this is a pretty steep slope, starts off at 3, right? 3, then 2, then 1, eventually hit 0, then -1, -2, -3 maybe, -2, -1, 0, slope 1, slope 2, back to slope 1, slope 0, -1, -2, -3. So imagine if you are graphing all these as y values from 3 to 2 to 1 to 0. And I'm going to kind of show how that's showing up. So here, that's a slope value of 3, then slope value of 2, then slope value of 1, then slope 0, -1, -2, -3, back to -2, -1, 0, then 1, 2, back to 1, 0, -1, -2, -3. So imagine you're just plotting all these numbers on an f prime graph. So that's what we're doing. We're not graphing the position of the function. We're graphing the slope value of the function. So that's why the graph looks a little different. Any questions here? Okay. So now let's graph our second derivative graph. Okay. So second derivative graph is going to look completely different as well. And I'm going to indicate a couple of points on my original function. So let's label this. So at -2 on the original function, I want you to label that point. And then at 0, I want you to label this point here. So there's a point of inflection at x equals -2 and at x equals 0. Okay. May not be super accurate, but just for purposes of this problem, it'll be nicer if we just have integer values. So if you look at this original graph, right? Concave down, then it transitions to concave up, but along the way, a point of inflection will have to occur for that transition to happen. So concave down, point of inflection, concave up, point of inflection, concave down. All right, so let's create our f double prime sign line. We know our points of inflections are at -2 and 0, so I'm going to put that onto my second derivative sign line. So to the left of -2, I'm experiencing concave down. Right? What I see is what I get here. Concave up. And then to the right of 0, back to concave down. Okay. Right, so here's my second derivative graph. So my second derivative graph, my y-axis is again changing its relationship. No longer is the y-axis representing position or slope. Now my second derivative y-axis is representing concavity, represents concavity value. So I'm going to label what I'm dealing with. Above the x-axis is where my original graph is going to be experiencing concave up. Below the x-axis is where my graph's going to experience concave down. On the x-axis, guess what? These are going to be what? Yeah, points of inflection. Or let's just say potential points of inflection, because it does have to cross, it has to change sign. So if it bounces off the x-axis, it's a critical point, but it's not point of inflection. But these are both points of inflection because we can clearly see there's a change in concavity at each of these intervals here. So we start off with points of inflection. Go ahead and plot -2 and 0 as x-intercepts. Right, where do we want our graph to live to the left of -2? Above or below the x-axis? What does this show here? Concave down, so concave down has to be below. So you're just going to have the graph rise to that point. Between -2 and 0, where do we want our graph to live? Above, right? So if it's above, it'll have to go up and come down because there's a point waiting for me. Now, some students find this confusing because they want to match the shape with what they see on the graph. The shape, though, is for the original function graph. It's not for the second derivative. So second derivative, you're just matching the location. Just make sure that it lives where it's supposed to live. Don't worry about the shape. So some students feel like, oh, wait, this is concave up. I got to make that shape look like concave up. The concavity, the shape is for the original function. It's not going to bear any meaning for the second or for the first derivative graph. Okay, to the right of 0, we want the graph to live where? Below, because I have concave down. So I'm just matching the symbols here. Okay. So here's my second derivative graph. Okay. I do want to connect this with power rule that we know how to get to the second derivative power rule wise. So this here is basically can be categorized as a degree 4, right? Because there is 3 change in directions here. The arrows are both pointing in the same direction. So imagine this is like around negative x to the 4th. This is not the full function, but this is at least the degree matches. Okay, so if I were to ask you, what is the derivative of negative x to the 4th? What would you say? Negative 4x cubed. Okay, so I'm gonna put that down here. Y prime equals negative 4x cubed, right? That's a cubic function. The graph that we put as f prime is a cubic function, right? So that matches with what we know to be true calculus-wise with power rule as well as graph-wise, right? So that's consistent. All right, let's go a step further. What's y double prime? Yeah, y double prime is negative 12x squared. That's degree 2. Degree 2 is a polynomial, sorry, is a parabola, and the parabola shows up in our f double prime. So power rule relationship matches with the graph relationship that we also did. Right. Now, most of the AP exam problems that you're going to see are going to start off here, where they give you an f prime graph, and they will ask you to create a version of the function graph and also create a version of f double prime graph. That's going to be the relationship. So that is how the test question is going to look like. And we'll do a lot of practice with that, where I give you an f prime graph, you're going to create a slope sine line, and from that slope sine line, you can then match the shape of the graph. So let me talk about that relationship back and forth, and then we'll try one on the next page where we're going to start with an f prime graph and build our way up. So this is what we're going to do with, if you're given an f prime graph, you're going to first identify your x-intercepts. Your x-intercepts are your slope zeros, and then you're going to label your f prime graph. Above is positive slope, below is negative slope. After that, you're going to place your x-intercepts onto your sine line. So -3, -1, and 1 will go onto your slope sine line. And then if it's above the x-axis, you're just going to indicate that with a positive slope. If it's below the x-axis, look at your indication. That's a negative slope. If it's above the x-axis, positive slope. Below the x-axis, negative slope. And then once we have our slope sine line, then we're going to sketch a version of this graph. As long as we can get the shape of the graph, that's all that matters. It doesn't really matter that your y-axis is up here versus down here. Your graph may be shifted. You may have a higher max and lower min, but as long as the shape of the graph matches, that's all we care about. So it doesn't have to live exactly here, but the shape needs to match, right? And if you just look at your arrows, just follow what the arrow is telling you, and then you'll be able to sketch your f of x graph. Now, moving on to f double prime. The way we find points of inflection off of the f double prime graph are the peaks and valleys of your f prime. Because we talked about how your point of inflection on the original function is basically, if you're on the roller coaster ride, it'll be where the ride experiences the steepest slope. So steepest slope could be like -3 or a +2. So if we're talking about the negative or the steepest places on the f prime graph, then the steepest places will be the max and mins of your f prime graph. So then from your max and mins, -1 and 0, or -2 and 0, you're going to place them onto your f double prime sine line. And now you're looking at the slope. Whenever my slope is becoming more negative, That's going to indicate to me where my original graph is going to be experiencing concave down. We don't want to look at the shape because we can't say, oh, this is concave up, this is concave down. That will be good if you're looking at the function graph. But if we're looking at the f prime graph, it's the slope that we have to look at. So negative slope will translate to concave down. Positive slope means concave up because this means my slope is moving in the positive direction. If my slope is moving in the positive direction, it's like this, right? -2, -1, 0, 1, 2 is going to have this behavior. And then a negative slope on the f prime graph is going to translate to a concave down. And then once we have this in front of us, then we can label our f double prime graph, concave up, POI, concave down, place our -2 and 0 onto our concavity sign line, below the x-axis, above the x-axis, concave up, and then below the x-axis. You may find this helpful as well. On your homework handout, there's this this thing called, this labeling called Morgan's method. This a couple years ago, one of my students put together this chart to kind of help her organize between the function derivative and second derivative. And so you might find this helpful. So it's basically under f of x, f prime, and f double prime, you have x and p, and you have 3 columns, and they're staggered. So x and p, then f prime starts at the m level, x and p, and then staggered down to x and p. This is most helpful at the f prime level. So the x represents x-intercept, the m represents max and mins, and p represents points of inflection. So this tells us that the x-intercept of your f prime is going to match to be the max of your f of x. All right. So the x-intercepts of your f prime is going to match up to be the max and mins of your f of x. All right. The max and mins of your f prime, your points of inflection, is going to match up to be the x-intercepts of your f double prime. And then the max and mins of your f prime is going to link up with the points of inflection of your original graph. So that's where this table, this chart, finds itself to be the most useful. If you're looking at the f prime graph, you can make sure that your function and f double prime is lining up in terms of the max location, the x-intercept, and the points of inflection. Okay, so let's go to the next page here, page 27, and let's try one problem where we are starting at the f prime level. Okay, so we're basically starting at the middle section of our previous problem, and we're trying to gather information about the f of x and f double prime. So first things first, let's go ahead and label what we're dealing with, right? And it's helpful to label because we have to keep reminding ourselves, this is not the shape of the original graph. This is representing the slope value of the original, not the position value of the original. So let's label. Anything that sits above the x-axis means where my original graph is experiencing a positive slope. Anything that's below the x-axis represents where my original graph is experiencing a negative slope. Anything on the x-axis is slope 0. Okay? We're going to start off with slope 0. So we'll create an f prime sign line. Okay? What can I place onto my f prime sign line? X-intercepts, right? X-intercept slope zeros, which are where? -4. Where else? -2 and 1. Okay. Okay. Don't look at the rise and fall of the graph. Look at the location. Is it above or below the x-axis? To the left of -4, what do you see? Below. So below translates to negative slope. I know it's confusing because it looks like, oh, it's rising, but it tells us that the slope is becoming headed towards positive value, but it's still in the negative region. So okay, between -4 and -2, where do you see the graph? Above. So there's my indication. There's my guide here on the left side. Between -2 and 1, below. And then to the right of 1, below. Yeah, still below. Okay. Let's go ahead and get the second derivative sign line out of the way as well, f double prime. So this chart tells us that the max and mins of your f prime graph is going to translate to the x-intercept of your f double prime. So basically, that's where the points of inflection is. The max and mins, the points of inflection of the f of x is the max and mins of the f prime, which will go as the x-intercepts on the f double prime. Okay. So where do you see the max and mins of your f prime graph? -3, where else? -1, where else? And 1. So there's an overlap, right? So 1 is an x-intercept, but it is also a peak of the graph. Okay, so -3, -1, and 1. So now let's look at the slope. The slope of my f prime is going to translate to the concavity of the original. So if I have positive slope, what is that going to mean? If I have positive slope on an f prime graph, that's going to mean concave what? I know you're tempted to want to look at the shape and say, oh, this looks like concave down, but this is not the original graph. So we got to look at the slope. So here my slope is becoming more positive. Therefore, that's going to translate to what? Concave up on the original. Yeah. Here, my slope is becoming more negative. If my slope is becoming more negative, that's going to end up shaping like what on the original graph? Concave down. Yeah. Positive slope. Concave up. Negative slope means concave down. Again, you have to fight that temptation to feel like, oh, wait, this looks like concave down, though. I mean, it's great if that were the original function, but this is not the f, this is the f prime. So the concave up, concave down is meant to tell you the shape of the original, not the shape of the f prime. Okay. All right, so we're going to sketch what the original function graph looks like, but this is what I want to do. I'm going to cover this up, because I think if we're looking at this, trying to sketch the function graph, we're going to end up copying the graph that we see in front of us. So I'm going to force ourselves to just look at this to sketch our graph. We're going to follow exactly what the arrows are telling us. The arrows are, if the arrow is pointing down, we want our graph to fall. If we see an x-intercept, if we see a tick mark, that means our graph is going to level off. It's going to flatten out for a moment. And then if it changes its direction, we'll follow that change in direction. Okay. So what do you expect at -4 on your function graph? If the graph is falling followed by rising? Relative what? Relative min. Okay. What do you expect at -2? Relative max. What do you expect at 1? Anything? No. Yeah. So the graph is going to fall. It's going to flatten out. It's going to level off for a moment, but it's going to continue falling. Okay? That's neither a max nor min. Now, if you're asking, wait, where do I put these relative max and relative mins? It doesn't matter. Okay. You can put them anywhere as long as your graph is end up shaping like this. So someone's graph may look higher or lower than another. Their max may be lower or higher than another. it doesn't matter as long as our graph is shaped. But for now, we can kind of just do this together. So if I see a relative minimum, I'm going to target a point that is lower. Okay, you don't have to. You can have it higher if you want, but it just gives me a target for me to move towards. At -2, I want a relative max, so I want to make it more dramatic. So I want my graph to be a little bit higher up. And then so I'm going to have my graph fall, rise, and it's going to fall to some x value at 1, but it's going to level off and continue falling. So I'm going to pick a point somewhere between. Now, if your max and mins, again, is higher or lower than mine, it doesn't matter, because in the end, I'm looking at the shape. If your shape matches with my shape, that's all that matters. So this is just a rough sketch. We're going to go back and give it the curvature of the graph. But right now, I just want to follow the path and just sketch out the path. So decrease to -4. Flattens out for a moment. That's true. Relative minimum. Rise to some y value of -2. Flattens out. Falls to some y value of 1. Anytime you see a tick mark, make sure you have the graph flattened out for a moment. It's leveling off. It's experiencing a slope 0 for a momentary time before it continues with the slope you'd see after that. So it's going to flatten out, and then it's going to continue falling. It doesn't matter how steep your slope is, as long as your graph is experiencing these slopes, is following the path of the arrows, that's good enough. Good so far? Now we're going to update this graph here, give it the curvature based off of concavity information. So -3, -1, and 1, wherever graph lands, go ahead and just plot this point. So this is going to be our graph, basically. Okay? We're not going to veer too far away from this path. We're going to go back and kind of update and give it a bit more curvature, but we're not going to create a new path out of this. Okay, so whatever you have here is basically you're retracing your graph basically when you do concavity information. So -3, wherever the graph lands at -3, go ahead and highlight that point. Yours may be higher or lower than mine, but at -1, wherever the graph lands at -1, go ahead and highlight that point. Wherever the graph lands at 1, go ahead and highlight that point. Now, between these points, we want our graph to experience a change in curvature. So now we can match the shape that we expect from these curvatures. Okay, now we're dealing with the f of x graph. We can do that. So what do we start off with? Concave what? Up. So we're going to give it that U shape. And then transition point of inflection. Now we're going to shift back to what? Concave down. Okay, so from point to point, we're going to give it that concave down shape. And then from -1 to 1, we want what? Concave up. Now, obviously, we can't do the full concave up shape because it's only this between this, but it's still considered concave up because we still have that portion of our U that's showing up. So even if it's not showing a full U shape, it is still considered concave up. But then it shifts back to what? Concave down. And here's a good way to double check. Your graph f of x should look nothing like your f prime. Okay? If your f of x graph ends up looking like your f prime, something is off. That means we probably end up looking at the f prime graph as we sketched. It's always good to, all three graphs should look very different from each other. Okay, let's create our f double prime graph. So f double prime graph is just purely based off your sign line. Let's label what we're dealing with here. Above the x-axis is concave up. Below is concave down. On the x-axis is my point of inflection. So we start off x-intercepts, right? Second derivative, your point of inflection are your x-intercepts. Okay. All you're doing is you're just threading the graph between these points. Don't look at the shape. The shape is not going to match what we have here. Okay. Match the location, but don't match the shape. Where do we want to start? Above or below the x-axis? Above. Has to thread through these points, right? So it's going to start above. Then it's going to be below, but it has to loop back up. Above, below. I know that you're going to be tempted to want to feel like, okay, this looks like concave down. I should make this concave down. And so some students end up making the graph shape like this. So, okay, the shape is for the function, not for the f double prime. So saving the easiest part for the end, all these characteristics, you're just pulling directly from your sine line. So increasing would be from -4 to -2. Decreasing would be from -infinity to -4, -2 to 1, and 1 to infinity. Relative max, -2. Relative min, and -4. Concave up, -infinity to -3, -1 to 1. Concave down, from -3 to -1, from 1 to infinity. Point of inflection, x equals -3, -1, and more. All right, so if you can create your sine lines, then your characteristics are easy because you're just pulling the information from your sine line. Okay, go ahead and try that, fill that out, and then we'll see if we can try one more problem, example 4, together. Okay, any questions? Okay, let's try number 4. So start by labeling your f prime graph. Your first order of business, can you get your slope and concavity sine line set up? If you can get those two set up, that's the hardest part of the problem, because then after that, you can just use the sine lines to kind of help give you guidance as to how the graph is going to be shaped. All right, so as you guys try number 4, I'll work alongside you guys. For your second derivative sine line, be reminded with this here, the points of inflection of your original function is going to show up as the max and mins of your f prime, which will show up as the x-intercepts of your f double prime. So the max and mins will go on your sine line of f double prime, as well as the x-intercept of your f double prime graph. Let's keep reminding ourselves that this is not the original graph. So we never want to look at, oh, this looks like concave up, then concave down, then concave up. We got to look at the slope. Okay, this you see a negative slope on the derivative f prime or g prime graph. That's going to translate to a concave down on the original. Positive slope, concave up. Negative slope, concave down. Positive slope, concave up. How do we feel about these sine lines here? That's the hardest part. You can get the sine lines down. Easier to move forward. Okay. After this, I'm going to purposely cover up my G prime graph because I want to force myself to just rely on these arrows for me to sketch my graph. I want my graph to rise, flatten out, rise, flatten out with a relative max, falls, flattens out, and rise again. So I got a relative max, a relative min, and I have nothing here. So your graph may be higher or lower than mine, but all we care about is, can we follow what the arrows are telling us? If the arrow is pointing up, we want our graph to rise. If the graph is pointing down, if the arrows are pointing down, we want the graph to fall. Give myself a target point. Relative max at 1. And down here. So my graph is going to rise, flattens out at -2 for a moment. Anytime you see a tick mark, you want your graph to level up. Okay. Rise until I hit some y value, relative max. And then falls. It's a relative min at 3. And then rises after that. I'm doing dotted line because I haven't committed to the concavity. I just want to pave the path for my graph. If all your graph is above the x-axis, that's fine. If all your graph is below the x-axis, that's fine. But are your movements the same? That's what I care. Okay, so points of inflection, -2, 0, and 2. Wherever your graph lands at -2, go ahead and highlight that point. Wherever your graph lands at 0, highlight that point. Wherever your graph lands at 2, highlight that point. Now we're going to retrace the graph with the proper curvature that we expect. So concave down, up into the first point of inflection. Then switches to concave up. Then switches to concave down. And then switches back to concave up. Okay, finally, second derivative graph. Let's label accordingly. Above is concave up, below is concave down. Point of inflection lands on the x-axis. So -2, 0, and 2. Don't look at the shape of the graph. Look at the location. This is only telling us whether our graph is going to live above or below. And it's going to be a simple graph. It's just going to thread through. You're not going to have a lot of curves. It's just going to really just snake through these points. Okay, so we're going to start above or below the x-axis. What does this tell us? Below, yeah. So has to come up to these points. Then it's going to end up above, come back down. So these anchor points kind of tell us where our graph has to eventually go through. From 0 to 2 is below, and then to the right of 2 above. Characteristics, you're just copying your sign lines and translating it into interval notation. Okay. All right, your homework, I put this on a separate sheet for you. So I have 35 to 38, 63 to 66, all on your worksheet. And then the key I attached to the very back. Okay. So just work through these pages, and this will be your homework. All right, come get your phones. All right. Oh, right. Just this. Yeah, so it's all on here, and the last page is the key.